Okay, next I'm very pleased to introduce our speaker today, Danielle Katz. Danielle Katz is a chief scientist at National Center for Computing Applications, a research associate professor in computer science, and in electrical and computer engineering, and in information sciences, and a faculty affiliate in computational science and engineering at the University of Illinois Urbana-Champaign. He is also a Better Scientific Software BSSW Fellow. Dan's interest is in the development and use of advanced cyber infrastructure to solve challenging problems at multiple scales. His technical research interests are in applications, algorithms, fault tolerance, and programming in parallel and distributed computing, including HPC, grid, cloud, and other platforms. He is also interested in policy issues, including citation and credit mechanisms and practices associated with software and data, organization and community practices for collaboration, and career paths for computing researchers. He received his BS, MS, and PhD degrees in electrical engineering from Northwestern University in Evanston, Illinois, in 1988, 1990, and 1994, respectively. His work is documented in numerous book chapters, journal and conference publications, and NASA Tech Briefs. He is a senior member of the IEEE and ACM co-founder and current associate editor-in-chief of the Journal of Open Source Software, co-founder of the U.S. Research Software Engineer Association, and co-founder and steering committee chair of the Research Software Alliance. Okay, so without further ado, also for questions, we'll take them at the end. Yeah, so just keep them in mind. But yeah, I'll hand it off to Daniel. So there you go.
Okay, well, thanks very much. Thanks for the opportunity to do this for the people that are here in this meeting, for people that are watching on YouTube separately. So as you heard, there's a bunch of things that I'm interested in related to software, and this talk is trying to combine a number of them and put them together in the context of making research software more sustainable, because I feel like that's really the goal that I'm actually interested in the end, is how do we take the investments that we make in research software and make that software more useful and have less duplication and more collaboration. So having said that, then let me go ahead and start. So I think that in general, people, scientists, researchers, I'm going to use science a fair bit, but I don't actually just mean science, I really mean scholarship, want to collaborate. And so I would say open science is the free sharing of scientific ideas, methods, and results. As I was saying before, it's not really just science. It's what in German is Wissenschaft, but we don't have a good word in English for this thing that's kind of science, but more than science. And this collaboration initially was done via people writing letters to each other and then writing books, and those books were mostly for other scientists. And then we got into, about 400 years ago, the idea of printed journals, and that expanded the audience of who could understand, who could collaborate. And then as digitalization happened, that expanded opportunities for sharing, as well as expanding what could be shared, not just printed materials, but not just words, but other things. So we also have the democratization of research and its public funding, as well as information sharing, like through bulletin boards and the web and other things. And those have also expanded the community and made it easier to share. And we have this idea that knowledge is a common good, a societal good, that I think a lot of people would agree with. I've been trying to understand where this open science term came from, and as far as I can tell, it appeared first in Science in 1882, but that open science at that point really meant the scientific method, or what we would call the scientific method today. It didn't really mean what we would call open science today. It seems like open science in its modern sense came around in the mid-1980s, as best I know. And it seems like the AAAS project on secrecy and openness in science and technology in 1984 was really the thing that started this modern movement of open science, or at least identified it and gave it a name. So even though we do want to collaborate, we also compete. And that's because we live in capitalist societies in general, and economics really drives our lives. It drives where we work in terms of hiring, how we support ourselves in terms of promotion, how we actually get funding to do science, to do scholarship in terms of support and recognition. What science we actually do often tends to be in areas that we think will lead to reward, whether that's explicit or implicit. And what students we work with also really is dependent on economics. And so economics can be defined as the science of allocating scarce resources to maximize the achievement of competing ends. But this doesn't always hold, particularly in science, because some resources can be increased, digital resources, for example, without really having a scarcity. So people then are kind of caught between these two things of competition and collaboration. And we can think of engagement as the way that people join together in groups to collaborate, with competition also kind of in the background. And so we can think of engagement then as meaningful and valuable actions that produce a measurable result. This is the idea of choosing when and where to come together to do something. And engagement then can be defined in terms of motivation and support minus friction, where motivation has two halves. It has an intrinsic part, that's all the things that are internal to yourself, plus an extrinsic part, which is things that are external to yourself, your job, your rewards, your recognition, your relationships, things like that. Support is what makes it easier to engage, relevance, timeliness, value. And friction are things that make it harder, like technology problems, user interfaces, time, access, lack of knowledge. So again, I think the main point here is that there are ways that we can define engagement, there are ways that we can define collaborations, and there's things that we can try to increase and things we can try to decrease if we want to increase engagement. If we're thinking about this other side, competition, and why we don't collaborate, there's a bunch of different reasons. One of them is that this sharing our work takes effort, and the immediate benefit of that effort goes to other people that we share with. Right? There's a long-term benefit to ourselves, but it's not necessarily an immediate benefit. People are often embarrassed about the details, for example, their coding practices, and that leads them to say that they don't want to share their code because they don't want people to see their code. Sometimes it's because you don't want to support others. Right? You've built some code that would be useful to others, but you're afraid that if you give it to them, they'll ask you questions and you'll have to spend time helping them. The mechanisms of sharing are new, and they're not the way we've worked traditionally. Metrics for evaluating products can be shared or underdeveloped, so we don't really have good reward systems built yet around this. There's intellectual property laws that are somewhat counterproductive to collaboration and sharing often. There's commercial entities who profit from restricting access to materials that otherwise could be shared. And then there's also nonprofit scientific societies that basically are really dependent on journal subscription fees to support themselves and the work that they do. And so they also have an incentive not to give things away for free, but to have some charge for things that helps them do other good activities. So having said that in general, diving into research software specifically a little bit, the reason that we care about research software, or at least the reason I care about it, is because it's important. And we can find that importance in three different areas. One is to look at funding, where we can see things like 20% of NSF projects over an 11-year period topically discussed software in their abstracts. 2 of 3 main areas in the Department of Energy exascale computing program really are research software activities, and this is probably $4 to $5 billion of investment. And about $300 million of NIH projects in the most recent fiscal year that I could get data for included software development as part of the project. We can also look at publications, and we can see that software-intensive projects are a majority of current publications, and the most cited papers are either methods papers or they're software papers. And you can often think of software as the implementation of a method. And then finally, we can just ask researchers. And when we've asked researchers in the US and the UK, we find that 90% use research software, about 2/3 say that they wouldn't be able to do their research without it, and about 50% develop software as part of their research. So I think the argument that I'm trying to make is that software is important to research, as seen in funding, as seen in publications, and as seen by just asking researchers. So what is this research software then? There's a few different ways we can define it. One is that research software is a component of instruments. Another is that research software actually is the instrument itself. A third is that research software is the thing that allows you to analyze research data. Fourth is that research software is the way that you present research results. Another is that research software is the glue that assembles or integrates existing components into a whole. Another one is that research software is infrastructure, or it's an underlying tool that gets used to do research. And then there's research software facilitating distinctly research-oriented collaborations, so a means of collaborating. So if we want to think then about kind of how do we put all these things together into a vision about research and research software, I would say that that vision would be that all research software that can be is open, that all research software is high quality and robust, that all research software is findable, accessible, and usable, and it's actually used by others for their own research, and it's cited when it's used, that all contributors to research software are recognized for their work and that they have good careers, and that all research software is sustained as long as it's useful. And finally, that all research is reproducible. So all of these things have overlaps, particularly in terms of incentives and policies, and all of them start with recognition of research software. So this, I would say, is the vision that I'm trying to work towards in a number of aspects, and I feel like it also is the vision that a lot of other people are working towards, at least parts of it, and overlapping parts that we can work on together. So one of the problems then is software collapse. And the issue here is that software stops working eventually if it's not actively maintained. The computational science software stacks that are used generally have a similar structure where we have on the bottom non-scientific infrastructures, things like operating systems and compilers and support code. On top of that is a scientific infrastructure, and that's things like libraries and utilities that are used across many disciplines. On top of that, then, is discipline-specific software, like tools and libraries that implement disciplinary methods and models. And on top of that, then, is early project or question or investigation-specific software. That's the software that does a computation using building blocks from those other levels, often in the form of scripts or workflows or notebooks, as well as small special-purpose libraries and utilities. And the issue is that the software in the stack builds and depends on all the software on all the layers below it. And any change that happens below it can cause the software to collapse. So if the operating system changes, then everything else may need to be adapted in some way to deal with that new operating system, for example. So this leads then to challenges. One of them is that research software is primarily developed and used for the purpose of research, to generate, process, analyze results within the scholarly process, as I mentioned before. It's increasingly essential to the overall research process, as was shown by funding and publications and researchers, but there are these challenges that we have. That software collapses if it's not actively maintained, software bugs are found, new features are needed, new platforms arise. This software development and maintenance is human intensive. We don't know how to automate this, and people actually just have to dig in and do it. And then there's also human challenges, which is that a lot of the software that's developed for research is developed by researchers. And these researchers know their disciplines really well, but they often don't know software best practices. And they're not rewarded for software development and maintenance, at least not in academia. And then finally, the developers who we have don't match the diversity of our overall society or even of user communities. So there's a lot of people that get left out and don't have an opportunity to get involved and create new ideas and new software. So if I put this together, then I'm going to define software sustainability as just the fact that the software endures. And the questions then that go along with that is, will the software continue to be available in the future on new platforms meeting new needs? And this can only be measured in hindsight. Right? We can say that software has been sustained. We cannot say that software will be sustained or that the software is sustainable in the future. Again, software development and maintenance requires active human effort. That human effort can sometimes be transferred or correspond to money, but not exactly. We can have projects that are entirely based on human effort, and that's things like community open source projects, and we know those can work. We can have projects that are entirely based on money, salary, commercial software, grant-funded projects, for example, we know those work. It's really hard to combine these two, though, because effort is not actually equal to money, and people are not purely rational. So if you have a project that has grant funding for some developers, and then you ask for volunteers to also work on the project, those volunteers may ask why other people are getting funded and they're not, for example. So how this actually gets put together is a challenging problem that we don't really have the right answers for yet. Again, to define research software sustainability in more words, It's the process of developing and maintaining software that continues to meet its purpose over time, which includes that the software adds new capabilities as needed by its users, responds to bugs and other problems that are discovered, and is ported to work with new versions of the underlying layers, which include software as well as new hardware. So that's really what I want to try to address, is how do we actually do this? How do we actually make research software sustainable? Some potential solutions are that we can try to do things that reduce the amount of work that's needed to do these pieces, to fix bugs, to port software to new platforms, to add features. We can do things that increase the amount of available resources. We can try to bring in more funding, more volunteers, more automated methods. And we can do things that do both of those, that reduce the amount of work and increase the available resources. Those are basically the three options that we have, and there's a bunch of different things that we can put into each of these options. So in the first one, if we want to try to reduce the amount of work that's needed, one thing we can do is to train developers better. And this involves finding and developing training material. And so Carpentries is an example of an organization that produces such material. There's also discipline-specific materials and language-specific materials. We can try to use best practices, which involves finding or developing those best practices. And again, Software Carpentry has some ideas on this, and there are incubators that do this as well. ESIP and Apache, for example, are organizations that have incubators for research software development. If we want to increase the amount of available resources, one thing we can do is to create incentives so that people want to work on the software to increase the number of volunteers. We can think about things like citations that help in existing career paths. I'm going to talk about that in one of three topics that I'll get into in a couple of minutes. We can think about adjusting existing career paths so that they better reward software work, whether those are postdoc, staff, faculty, people in national labs, people in industry, people in government. We can think about new career paths. And I'm going to talk about this in the second of these three new topics in a couple of minutes. We can also increase the amount of available funding, and we could do that by making the role of software and research clear to research funders, whether those are government agencies, philanthropies, or industry, and then clearly making the case for them to increase funding for new software and to provide funding for software maintenance. And if this is government or philanthropies, they're probably doing this for the common good. If it's industry, they're doing it because it's going to help them do whatever they're trying to do better. We can also think about seeking institutional resources. So for example, if we have software that's developed at my institution, at NCSA at Illinois, if we can make an argument that that software is sufficiently important to NCSA, either operationally or reputationally, then I can try to argue for internal funds being used to help maintain it. And then finally, if we're thinking about both reducing work and bringing in new resources, one good way to do that is trying to encourage collaboration. And if you can use the work of others rather than re-implementing something yourself, that reduces what you have to do, even without assuming that the collaborators are going to come in potentially and help you, which also may happen. If others are using your software and contributing to maintaining it, then you have less work that you need to do, is the other side of this. But in order to make this work, software has to be developed from the beginning to be modular and reusable, which is really hard. And it also has to be clearly documented and explained to potential users, even those in fields other than the developers. And this is maybe even harder. The software team also then has to put effort into engaging and working with the potential user and contributor community. And this is something that a lot of software developers don't see as something that's necessarily appealing to them. They want to focus on the software, not the users. So we need people that are interested in both sides. So overall, a way to do this then is to make the software findable, accessible, interoperable, and reusable, and FAIR is the acronym that goes along with this. And then that's the third thing that I'm going to talk about as we go forward, and the third out of three. So to go into the first one then, about citation. In 2015 to 16, we started a working group on software citation. And in that group, we documented the differences between software and data because data citation was already starting to take off. And we defined a set of software citation challenges. And we did that in two different documents. And then we ended up, over that 2-year period, creating a set of software citation principles and publishing those principles. And those principles are, first, importance, that the software should be considered an important and citable product of research. Second, credit and attribution, that the purpose of software citations is to facilitate giving credit and attribution in a scholarly way. Third, unique identification, that the software citation should include a method that is machine actionable, globally unique, and interoperable and recognized by a community. Fourth, persistence, that the software citation should endure even if the software itself isn't, that the identifiers and the metadata are long-lasting. Fifth, accessibility, that part of the purpose of a software citation is that it actually gives you access to the software itself and the metadata tied to it. And sixth, specificity, that the software citation should facilitate identification of an action to the specific version of the software that was used, not just the generic name of the software overall. So having done that and built those principles, we started another working group in 2017 that's really just wrapping up now, called the Software Citation Implementation Working Group. And what we thought we were going to do was to write out a little bit of detail that was needed to actually implement those principles, and then to coordinate some work going on to do that, and to work with communities that wanted to do this. And we quickly realized that that small amount of detail wasn't actually small, and that making scattered progress wasn't sufficient, and that the underlying challenges weren't being addressed. So we wrote another basically document to try to lay out what all of those challenges are in terms of implementation. And they include things about the complexity of software types and identifiers and where metadata is stored, as well as social challenges that are basically the groups need to work on implementation in their own context. And they need to run pilots that establish norms in those contexts and then come together and make those norms more general across different communities. So in response to the challenges, we've done a bunch of different work. We had a guidance task force that produced a guidance document for paper authors who want to cite software, and for software developers who want to make their software citable. We had a task force working in a project called Code Meta. Code Meta is a project that was trying to understand metadata for software. It built a crosswalk of existing metadata standards and then developed its own standard to describe software based on the kind of the union of those crosswalks in some sense. The task force updated the Code Meta standard. It's described everything in Code Meta using schema.org properties. And it's basically turning Code Meta into a community group with governance and turning the actual metadata part into schema.org. So it's standardized and we don't have to worry about that part. We also worked on registries, the places that software gets deposited, and we created a best practices document for software registries and repositories that want to hold software, and turn that into a community that is continuing in a group called SciCodes, and that's a consortium of scientific software registries and repositories that's open for anybody to join that's interested. The journals task force that we ran worked with publishers to provide them with generic guidelines, and they could then turn those generic guidelines into specific guidelines for their journals and conferences and their communities that used community accepted language and community accepted examples. We published that as a document with a bunch of different publishers as co-authors, and there's an industry publisher group called Chorus that is tracking the different software citation policies from a set of different publishers at this point and updating it at least once a year. We're also working on publication processing, and this is almost done but not quite done, which is effectively when you submit a paper and you have a citation of software, you're putting it in some format. Eventually, it has to go through a bunch of different processing and get to an index that helps the software producer understand who cited their software. And that process has some problems right now, and we're trying to provide some guidance for journals that help them fix those problems and make this process work more smoothly, so that people who develop software actually can count the citations and understand how their software is being used. And then finally, we considered an institutions task force, with the idea being institutions are places where people work, like universities. The goal of this task force would have been to affect policies and practices within those institutions, how they encourage software citation, how they use citation information in hiring and promotion, to collect and share examples to help form communities, but we didn't have enough interest to actually do this. So this is kind of on hold at this point. And then finally, we had an activity that tried to look at all of this last summer and tried to say, what have we done? What else needs to be done? Who can do it? And there was a workshop in Boston last summer that addressed this, and there's a report available. As of May of this year, earlier this month, we've completed the working group, but the community is interested in continued discussion, and we're currently writing a blog post to suggest topics and venues for that continued discussion to happen. I should have mentioned earlier, there's a DOI at the bottom of all these slides, and all these links that are in the slides you can click on if you get the slides from that DOI. Okay, so since I was talking about citation, I also just want to briefly mention the Journal of Open Source Software, JOSS. JOSS is a developer-friendly journal for research software packages. We say if you've already licensed your code and have good documentation, it should take less than an hour to prepare and submit your paper. Everything about JOSS is open. The submitted and published papers are entirely open access, free to submit, free to review, free to read. Where the code is itself is up to the authors. The review process is also completely open. It's the authors know the reviewers know the authors, the editors know both. And the code for the journal itself is also open source. So if you want to create your own version of a journal like this, you can do this. This code has been reused for the Journal of Open Source Education, and it's also what's used for the proceedings of the JuliaCon conferences. What you can see here is that we've been growing in terms of the number of papers published since we started. Sorry, I should say that the JOSS papers are archived. They have DOIs, they're cited. The first paper was submitted in 2016 at the beginning of this chart. In 2017, we had, a year later, we had about 110 accepted papers and 50 under review. As of a couple of weeks ago, we had a little over 2,000 papers accepted and about 230 that were currently in review. Current publication rate, as you can see, is about 1 a day, about 30 a month, but we're kind of slowly growing. We were growing quite quickly until the pandemic, where there's kind of a gap where we shut things down for a little while. And then when we reopened, we've had much slower growth since then. When we started, we had an editor-in-chief and 11 editors, and today we have 1 editor-in-chief, 7 associate and track editors-in-chief, and one of those, 69 editors, and 35 editors who have finished terms and have stepped down. JOSS is also a community, and so it's interesting to think about how cultures change, and this is often based on a combination of rules and incentives. JOSS practices, I believe, have influenced reviewers and developers in terms of thinking about what's good and what's minimally acceptable. This is similar to what ROpenSci has done in the R community. And for JOSS, the minimum criteria for successful review has changed over time as community best practices have developed. So our guidelines on packaging and testing and CI and documentation have gotten stricter over the 7 years that we've been doing this now. We also are applying open source software practices effectively to how we run the journal. So we're trying to make all the processes as open and collaborative as possible. And so JOSS effectively is providing rules about software, and at a high level, it's trying to nudge incentives by giving a reward for publishing software. We'd like the accepted papers in JOSS to effectively be seen as accepted papers in the rest of the scholarly system. So faculty members and others get credit for their software in the same way they would get credit for a paper. It's worth mentioning, if the software is being cited directly, which is what I was arguing we want to move towards previously, JOSS papers actually wouldn't be needed, but the JOSS review process and the JOSS community would still have great value. And so we'd have to figure out a little bit of a way to have reviews applied to software that's not a paper. But I think we may be able to do that, and that may be where we're going in a few years. Okay, so the second topic then is on career paths and research software engineers. Research software, again, comes from research in large part. It seems like this has happened from the beginning of computing, as far as I can tell, and I'm eager to hear other opinions, and I'll correct slides for the future. I think software has appeared around 1948. It seems like research software appeared just a couple of years later, first in weather in the early 1950s. The idea of software engineering seemed to start in the late 1960s, and it was mostly initially applied to operation software, like operating systems and NASA flights, for example. As I mentioned earlier, again, the researchers, often faculty, for example, generally don't really know good software practices. That's not what their expertise is in. We have software engineers who do know good software practices, but they generally don't understand the context of research. And then we have students and postdocs that are kind of in the middle in some sense. They generally don't start off knowing good software practices or their research area, but by the time they understand both reasonably well, they generally graduate and they go somewhere else. Sometimes postdocs do stay around and sometimes they join the staff of an institution like a university. Sometimes they're officially considered staff. Sometimes they're just considered a postdoc for a really, really long time. But overall, we do get to the point where we get staff who have a research understanding and software engineering skills, and they develop over time in a lot of institutions. So we can think about this then in terms of differences between the craftsperson and the scholar. A scholar is an archetypical researcher who's driven to understand things to their fullest capability. They work on intellectually demanding problems, and they do it in a curiosity-driven way. Right? They work on a topic until they have enough understanding of it, and they typically pass that understanding on through teaching or through documentation or through writing a paper about it. A craftsperson, on the other hand, is somebody that's driven to create and leave behind an artifact that really explains what they've done, that represents what they've done. They feel pain when they make things that are fragile or ugly. They prefer to make things that explain themselves well. And they do work that requires patience and have pride in doing their job well. Scientific software requires people who combine the best of both of these roles. And I'll just mention, this is from a blog that was written in 2012, and this is really when this idea kind of started about research software engineers. And so research software engineers, then you can think of as existing in a space where software engineering is one axis and research is the other axis. And we have traditional software engineers who are really strong in software engineering, but not necessarily in research. We have really strong researchers who are good at research, but not necessarily software engineering. We have a bunch of people who are researcher developers who are quite good at research and are okay at software engineering and can get by. But the idea is that we have research software engineers who are really more in the middle here and have better software engineering experience, but understand research as well. And this is kind of a cloud. It's not a single place that they sit, but they're kind of somewhere in this middle space. In 2012, there was a workshop in the UK called the Collaborations Workshop. And what they discovered is that there were already a lot of people at their universities, the universities that met, doing this kind of work, that were doing this work that today we would call research software engineering. But they had no common title. They looked and they discovered there were 194 different job titles they could find for people that were basically doing that same work. And so they decided research software engineer would be the title that they would come together on. It wasn't necessarily the one that everybody thought was the best one, but it was the one that everybody agreed was good enough to go forward with. They decided that there wasn't really any community. These people didn't really know each other very well. And so they started forming initially an association in the UK, which has turned into a society in the UK and a bunch of other associations and societies in other parts of the world. And this wasn't a profession. And so this group decided to start thinking about career paths and structures to turn it into a profession. So in the 10 plus years that we've had research software engineers, again, the idea of this was born in the UK, and by late 2013, the UK Research Software Engineering Association had formed with about 50 members. It's now a professional society with about 700 dues-paying members and about 4,600 members overall. There also are similar associations in Belgium and Germany and the Netherlands and the Nordic countries, Australia and New Zealand. And there's one in the US as well, USRSE, which has about 1,700 members currently across universities, national labs, and industry. And there's new associations forming in Africa and Asia today. These associations work on local issues collectively, and then they can coordinate across associations when there are global issues as well. And just to kind of show what this looks like, we've got now a bunch of countries that have these red associations, and we have these kind of more pink areas where there is work going on. And then we have gray areas where we need to do more work to kind of spread this message and spread this community. The advantages of research software engineers are that they lead to better software and more mature project management aspects and structures. They lead to ideas about team organization and work organization and software organization and coding practices, and try to standardize those in projects and professionalize them. And this then ideally leads to better and more sustainable code and more efficient group coordination. They also lead to institutional memory. Because research software is becoming more important and complex and costly, the expertise about it is valuable. And RSEs, as somebody in a university or an institution staff, have longevity beyond individual projects and students. And they're often also mobile across different disciplines and domains, so they can translate knowledge and artifacts across communities and take practices that work in one area and bring them into another area. They also build community expertise. Because RSEs typically work on grant-funded projects, and those projects typically have less than one full-time equivalent RSE in them, these projects have a shorter duration than staff careers, and this leads to some kind of matrix management with RSE groups often, where there's a PI axis that changes over time and is funded by the different projects, and then there's a group manager axis, which is fixed and funded by overhead or taxes on projects or the institutions. But effectively, this leads to people in a place where they can have somebody that's concerned about their career and somebody that's concerned about their project, and they can work on both and grow in both over time. This leads then to a pool of experts and expertise in an RSE group. And these RSE groups typically welcome others with shared interest, even if they're not in the group, like grad students, faculty, others who are just interested in making their software better for research. Okay, and then the last thing that I'm going to talk about is FAIR for research software. So in 2016, an article was written about the FAIR guiding principles for scientific data management and stewardship. And this article and these principles were intended to ensure that data are shared in a way that enables and enhances reuse by humans and machines, quite a laudable goal. And the principles are in 4 parts. There's findable, how data is made findable, which talks about things related to the data itself, as well as the metadata about the data. Things about accessible, which is how do you actually access the data? And again, there's questions about the data itself as well as the metadata. Interoperable, how can you use the metadata and the data with other metadata and data? How to use kind of common practices to describe it. And then reusable, which is that you have enough attributes about the data and the metadata that you can get to it, you understand it, you know where it's come from, and it meets community standards. And this is partly because it's an idea that caught on, partly because it's a clever acronym. It has become quite accepted in a lot of different governments and a lot of different communities that data should be fair. If we think about FAIR beyond data, these principles at a high level say that they are intended to apply to all research objects, both those used in research and those that are research outputs. As I mentioned before and kind of showed you, the text in those principles often includes meta in parentheses data, and that's shorthand for metadata and data because the people writing this wanted to be very concise. The principles themselves are applied via dataset creators and repositories. You can think somebody creates a data set, they give it and some metadata to a repository. The repository then makes it findable and accessible. And so the creators and the repositories together are responsible for creating, annotating, indexing, preserving, sharing the data sets and their metadata. As I kind of hinted, this assumes that there are separate and sequential roles between the creator and the publisher or the repository. Right? Somebody builds the data set, they turn it over to a publisher repository, the publisher repository shares it. But if we think about objects that aren't data, they can often be stored as data, but they're not just data, thinking of software as an example. The high-level goals of making, let's say, software findable, accessible, interoperable, reusable are the same, but the details and how they're actually implemented depend on how those objects are created and used. Thinking of software being, let's say, written as open source or written by a company, where the software is stored and shared, and how the metadata and where the metadata is stored and indexed about the software. So that seems to imply that there's work that's needed to define and implement and adopt these data principles for other kinds of objects, software, for example. As I said before, the FAIR principles are intended to apply to all kinds of digital objects, but the EASC task force in the European Union in 2020 had a set of 6 recommendations. One of them was to recognize that FAIR guidelines will require translation for other digital objects and support such efforts. And the French National Committee for Open Sciences, Free Software and Open Source Project Group specifically said that software has a nature that is different than data, that software is not just data, and that we need to work on it differently. So what our working group did was to focus on the adaptation and adoption of the FAIR principles to research software. And the reason, again, is that software is not just data. It's executable where data is not executable. Data in general provides evidence where software provides a tool. Software is a creative work, and scientific data in a very general sense are facts or observations. You may be aware that software can be copyrighted. Scientific data as data cannot be copyrighted. They end up leading to having different licensing and copyright practices around them. They're treated different legally. Software suffers from software collapse, where data really just has the issue that the bits may not be readable. The lifetime of software is generally not as long as that of data, although that's not always the case. And one of the big issues is that for open source software, there's no natural sequential creator and publisher process as there is for data. And there's no natural publisher. If you're building software in GitHub, for example, there's not really a publisher where you declare you're done and then somebody else takes it and they're responsible for it. It's kind of always you for the whole time. GitHub may help you, but GitHub also is not archival, and it's owned by Microsoft, who provides it as a service, but it may go away in the same way that previous repositories have gone away. So the FAIR for Research Software group then was a working group that defined a set of consensus FAIR principles for research software. There were 9 of us that led this group, and we did this under 3 different organizations, Force 11, which is a group that focuses on research communication and e-scholarship, the Research Data Alliance that focuses on data, and the Research Software Alliance that focuses on software. We first had to define research software in this context, and what we did was to say that it includes source code files, algorithms, scripts, computational workflows, and executables that were created during the research process or for a research purpose. There are additional software components like operating systems and libraries and other things that are used in research, but were not created during or with a research intent, and we would call those software in research, but not research software. And this differentiation varies between disciplines. So just for example, I've said that the operating system is typically research in software, but not research software. It's typically software in research, but not research software. But if you're a computer scientist doing work in operating systems, then your operating system is research software for you, even though it may not be for a computational chemist that's going to use it as a product later. So it's a little bit tricky to define this. The FAIR for Research Software principles that were published last year are at a high level similar to the FAIR principles for data. I'm here writing them out, and I'm using italics to indicate the things that are different, and I'm going to just talk about those briefly and not talk about the things that aren't in italics. So in terms of findability, two of the real issues here are related to identifiers and the fact that there is both versioning that happens in software in a way that's different from data, and granularity that happens in software that's in a way that's different than data. If you think about software, you could think about a project. A project has versions. Those versions have source code. They have issues. They may have design documents. The source code may be in files, maybe in directories first and then files, and each file may be thought of as having lines or tokens or something else. So there's a lot of different levels of granularity that you may want to identify. In terms of accessibility, there's really no real differences other than just saying software and metadata rather than metadata. In terms of interoperability, there are a lot of differences, and this is really a completely different idea. And what we've chose to say is that software interoperates with other software through exchanging data or metadata, or through interaction through APIs that are described in standards, and that we want to make sure that those things are done in standard ways for communities and that they are referenced appropriately. And in terms of reusability, we have the issue that software usability might be that it can be executed, and that's important to start with, and reusability might be that somebody else can understand it, they can read it, they can modify it, they can build on it, or they can incorporate it into other software as well as they can execute it. So that means that software is dependent on other software, and that that dependency is really a difference from software to data. So these principles were published. We've turned the governance of this activity, the interpretation of the principles and future revisions over to a different group, the Research Data Alliance Software Source Code Interest Group. We've published a survey of adoption guidelines from organizations that are interested, as well as studying how those organizations are doing this and why they're doing it. And we're left with the issue that FAIR for Research Software exposes some of the same ecosystem gaps that we talked about for citation, related to metadata archiving and versioning. As I said before, the creator and publisher sequence doesn't really apply often for open source. We don't necessarily know where metadata should be stored, if it's in the code repository itself for open source, but if it's for closed source software, where is it? And do we use archival repositories, or do we use registries? Where code is archived is also a challenge. As I mentioned before, GitHub and GitLab are not archival. They don't have any preservation aspect to them. We have registries that are not archival as well. We have repositories. There's something called software heritage, which is interesting to look at if you haven't seen it. That's kind of like the Internet Archive for open source software. It's aimed at trying to preserve a version of all changes of all open source software over all time. And then we have the fact that different use cases for software require potentially a specific version or the latest version or all versions, depending on what level of granularity you're interested in and what you're trying to do. So there's also a lot of work beyond FAIR, right? FAIR is findable, accessible, interoperable, reusable again. It doesn't say anything about the quality of the software. It doesn't say anything about the correctness of the software or the reproducibility of the work done with the software, or even the openness of the software. So just to kind of wrap up, having talked about those three things, I do want to just briefly mention the Research Software Alliance as a context activity and as something that you may be interested in getting involved in. Research Software Alliance has a vision that research software and those who develop it and maintain it are recognized and valued as fundamental and vital to research worldwide. And the mission of RISA then is to advance the research software ecosystem by collaborating with key influencers and decision makers. It was founded in 2019. It's a fiscally sponsored project by Code for Science and Society. And it recently has been involved in co-developing the FAIR principles I talked about, in talking about diversity, equity, and inclusion best practices, in doing a global mapping of the international research software community landscape, and then recently expanding it, in gathering global research software funders together to set an agenda for what sustainable research software means for them and how they can address that. And that's led to a draft declaration called Adore Software that we hope will be signed towards the end of this year. A declaration on funding research software sustainability signed by research software funders. As well as having collaboration, RISA having collaboration in specific issues that address the global research community. So if you're interested in this, you can sign up to receive the RISA newsletter. You can join the RISA Slack. You can add to a database that we have of open funding calls for research software. And you can join task forces that are focused on specific activities. So having said all that, a little bit quickly, just to try to wrap up, where we are now is that research software is increasingly important to research. Citation is the accepted mechanism for scholarly credit in academia, and software citation is beginning to be accepted with uptake from researchers, publishers, librarians, etc. Software papers are partially a placeholder for software citation, but they also have an important community function. Research software engineers have been recently recognized as an official role, but there's a long history of people doing this work from long before it had a name. And we're now building community around this and making a case within various institutions and funders for formal career paths. The FAIR data principles set out a good goal to share data to enable and enhance reuse, but there's work needed to apply this to research software, both open source and closed source, to fulfill the open science concepts. We've created a set of principles with about 500 people involved in about 60 different events. And there's now work underway to create guidance, adopt those principles, define governance. And the next steps then will be to create metrics and widen adoption. So finally, to close, there's things that you can do. You can promote software sharing and credit. And you can do this by, when you're an author of a paper, to be sure to cite the software that you use. When you develop software, make it easy to cite. When you review, whether you're reviewing work for a journal, for a conference, for a funding proposal, demand that software be cited in those documents that you're reviewing. And work to make your own software fair. Follow the FAIR principles as much as you can. You can support research software engineers. You can do this by just supporting the software developers and maintainers in your own organization, and think about how your organization does this, and see if there's a way that you can change it. If you're involved in reviewing somebody's promotion case, reviewing hiring, you're on a hiring committee, things like that. Think about how software is being recognized in those activities and try to raise it as an issue that should be considered. And US RSE and the Society of RSE in the UK are places that you can go to talk about this and work with others. As I said, you can work to make sure that software work is included in hiring and promotion. All of these activities are open communities, open science, open software, FAIR for research software, although that one's really finished now. Citation, which is kind of finishing as well, the RSE community and RISA. So you can join one of these communities. And finally, you can try to raise the awareness of research software as a key element of research. Right? Research software is not business software. It has different goals, it has different incentives, it has different methods, different practices, different workforce, different education. When people talk about software, you can highlight the fact that research software is important, and it really is a key element of research. And so with that, I will end by just giving some credits. Arvind Smith and Kyle Niemeyer and I co-led the initial software citation working group. Arvind is also the editor-in-chief of JOS. Neil Chu Hong and Martin Fenner worked with me in co-leading the software citation implementation working group. There's a bunch of different people that have been involved in RSE discussions with me over time, a bunch more people that have been involved in the FAIR for research software work. And then finally, a bunch of other people that have made me think differently about the way I've presented some work and the way I've thought about it and done it. The Better Scientific Software project that was mentioned in the introduction, that's given me a fellowship that helped me do some of the citation work. And if you're interested, I have a blog where I'm writing less and less frequently, but still occasionally, as well as a Mastodon channel that I tried to post to fairly recently. And with that, I will stop and see what kind of questions and discussion this might lead to. So thank you very much.
Great, thank you. I'm gonna stop recording and then